Hi dear students, this is Dr. Samir working as Assistant Professor in Department of Mechanical Engineering in KITSW. I welcome you all for today's session on additive manufacturing. Today we will be talking about the RP applications in biomedical industry. RP is the short name for the rapid prototyping. Rapid prototyping is nowadays more oftenly it is called as additive manufacturing. Additive manufacturing has immense applications in various industries. It can be aerospace industry, it can be automotive industry, it can be jewelry industry, it can be coin making industry, whatever we take, the RP is applicable to the particular industry. In today's session, we'll be talking the additive manufacturing applications in the field of biomedical. Let us start today's session on the biomedical industry. From the manufacturing of medical devices and creating customized implants and prostheses to surgical planning and education, RP can be applied to enhance medical applications and healthcare delivery. With the use of additive manufacturing, we can produce the medical devices and also we can create the customized implants. The word customized can be understood that each and every human body has different sizes and shapes. So it is not possible to produce the implants in the mass production. So we need to take the scanning of the part that we are going to manufacture particular implant. We need to take the CT scans, the MRI scans. Based upon that, the data has to be transferred into the 3D CAD system. Then from 3D CAD system, it has to be supplied into the additive manufacturing machine. Then the parts are manufactured. So this process of creating the implants specifically for each person, we call it as creating the customized implants. And the prostheses. Prosthesis is meaning for different limbs or the artificial limbs that we use for the human organs. We can also plan the surgeries and also the education. The medical education can be easily understood by the application of rapid prototyping. So we can say RP can apply to enhance the medical applications and the healthcare delivery. In the coming session, we will see few of the examples related to the additive manufacturing's valuable role in biomedical industry. The first example that we talk is the operation planning for cancerous brain tumor surgery. In a case study, a patient had a cancerous bone tumor in his temple area. And because of that, the surgeon would have to access the growth via the front through the right eye socket. The operation was highly dangerous as damage to the brain was likely, which would result in impairment of some motor functions. In any way, the patient would have lost the function of right eye. However, before proceeding with the surgery, the surgeon wanted another examination of the tumor and tumor's location, but this time using a three-dimensional plastic replica of the patient's skull. So here we are talking about an operation planning for a cancerous brain tumor surgery. If you can see, there was a patient who has a tumor in his left temple side area. So these are called the temples. So the patient had a tumor uh, in his temples, whether it is left or right. We have two temples. So the patient was having a bone tumor in his temple area. So that tumor was from the bone. So these are called the temples. As we can see it in the slide, this is the temples and this is the temples. And here we can see an image of the tumor from the bone temple area. Now the surgeon wants to perform the surgery to remove that tumor from the temple. The one way to do that was to do the surgery from the eye socket. If the surgery is performed from the eye socket, the patient would lose his eyes. So doctor wanted to view the 3D replica of the patient's skull, and the 3D replica was manufactured using the additive manufacturing process, and at the exact the profile of the skull was manufactured using this additive manufacturing. By studying the model, the surgeon realized that he could reroute his entry through the patient's jawbone, thus avoiding the risk of hammering the eye and motor functions. If the operation was performed through the eye socket, as shown in the figure, this is the red arrow indicates the eye socket. If this operation to remove the bone tumor from the temple area through the eye socket would also lead to risk of hammering the eye and also the motor functions. The motor functions of a human are generally walking, talking, doing some basic functions of a human body. We call them as the motor functions. And eventually, the patient lost one tooth and of course the tumor. So when the doctor has studied the plastic model of the patient now could reroute the surgery. Instead of going through the eye socket, the doctor wanted to perform the operation through the jaw where he could reduce the risk of hammering the eye and also reducing the risk of damaging the motor functions. So with the development of the 3D skull, he could analyze the patient's uh, tumor in the temple and he could reroute the surgery by doing it through the jaw. The only thing, the damage that happened to the patient was he only lost his one tooth. It would have been a better idea instead of losing an eye. So thanks to the additive manufacturing here. The plastic RP model used by the surgeon was fabricated by the SLA from a series of 2D CT scans of the patient's skull. So the rapid prototyping model, which was used by the surgeon, was fabricated by SLA. SLA stands for stereolithography apparatus. This is one of the additive manufacturing methods using the liquid resin. We call it as the classification of liquid-based rapid prototyping, where a photopolymerization process is used to cure the liquid resin upon solidification when it is exposed to the high temperature lasers. So the series of 2D CT scans of the patient's skulls were taken initially while developing the skull of the patient. In this slide, we can see the skulls manufactured using different additive manufacturing processes. In this skull, here we can see the 3D printed skull, which was manufactured using SLS, that is centering method. And here we can see the 3D printed skull was manufactured using SLA. And another example is a planning reconstructive surgery with RP technology. In one of the examples to how this planning a reconstructive surgery with RP technology can be seen with an example that due to a traffic accident, a patient had serious bone fracture on the upper and lateral orbital rim in the skull. Here we are seeing a patient who had suffered a traffic accident and he was seriously injured with a bone fracture on the upper and lateral orbital rim in the skull. To know what is the lateral orbital rim, if we take the skull points of fixation, the arrow shows in the first diagram, we call it as the lateral orbital rim. The upper part of the lateral orbital rim, this is the exact location of the fracture of the patient in the traffic accident. We have the other points of fixation in the skull as well. The second image, we call it as buttress of zygoma. Third picture represents the infraorbital rim and buttress. So the patient that we are talking in the example is the lateral orbital rim. So in the first reconstructive surgery, the damaged part of the skull was transplanted with the shoulder bone, but shortly after the surgery, the transplanted bone had dissolved. So earlier, the reconstructive surgery was done on the patient with the shoulder bone, transplanted with the shoulder bone on the damaged part. But shortly after the surgery, the transplanted bone had dissolved. And thus, it was necessary to perform another surgery to transplant an artificial bone that would not dissolve. So here comes the picture, the application of additive manufacturing. So the conventional procedure of such surgery would be for surgeons to manually carve the transplanted bone during the operation until it fitted properly. So one of the methods that the surgeons conventionally use is that they would manually carve the transplanted bone during the operation, and they would spend hours in the surgery in the operation room until it gets fitted properly. So this operation would have required a lot of time due to difficulty in carving bone and let alone during the surgery. By using rapid prototyping, a SLA prototype, that is the stereolithographic apparatus prototype of the patient's skull, was made and then used to prepare an artificial bone that would fit the hole caused by the dissolution. This preparation not only greatly reduced the time required for the surgery, but also improved its accuracy. So when the rapid prototyping had come into the picture, one of the methods to produce the prototype was the SLA. Here, the surgeons had made use of the SLA prototype of exact replica of the patient's skull was made. Then they could easily prepare the artificial bone that would fit the hole caused by the dissolution. Staying with the planning reconstructive surgery with RP technology, in another example, here we'll see In another case involved at Kyoto University Hospital of Japan, a 5-month-old baby had a symptom of scaphocephaly in the skull. Scaphocephaly is the tendency. If you can look at in the slide, the baby had scaphocephaly, that is both head. The figure 1 is the normal features of the baby, and this would give us the normal feature of the skull, which is shown in the figure A2. When coming to the figure B1, due to the scaphocephaly, the skull was extended, so it has bolted at the end and at the front. So due to that, the skull was bulged due to this effect. So coming to this scaphocephaly, it is a Greek word for both head, and the synonym is dolichocephaly. In that, dolicho means Greek for elongated. So in the Kyoto University Hospital of Japan, a 5-month-old baby had the symptom of scaphocephaly in the skull. This is a condition that may lead to serious brain damage because it would only permit the skull to grow in the front and rear direction. So during the growth of the baby, the skull would further grow in the front and the rear direction. Now, this required a procedure to take care of the skull part and reconstruct it so that when the brain grows, as the baby grows, the skull does not suppress the brain. So here, the procedure required was to take the upper half of the skull apart and reconstruct it completely so that the skull would not suppress the brain as the baby grows. Careful planning was essential for the success of such complex operation. Firstly, the prototype of the skull was produced and amputation lines were drawn on the model. Secondly, a surgical rehearsal was first carried out on the model with the amputation of the skull prototype according to the drawn lines, followed by the reconstruction of the amputated part. In this case, the rapid prototype type of the skull provided the surgical procedure with 1. A good 3-dimensional visualization support for the planning process. 2. An application as training material. 3. A guide for the real surgery. So in order to plan this surgery, it was really difficult to do it on the baby, on the 4-month-old baby. So the rapid prototyping here was useful in preparing the exact dimensions of the skull of the 5-month-old baby. Then the lines were drawn, and according to that, the skull was amputated by the lines drawn on the skull. So this operation, this rehearsal had 3 effects. That is, a good 3-dimensional visualization support for the planning process. So the 3-dimensional part has provided a very good visualization support for the planning process. Second thing, an application as training material. Here, the junior doctors or the surgeons have had an application as a training material and also a guide for the real surgery. If they have to perform really in practice, how would they do it? So it also served them as a guide. So in this slide, Here we can see the scan images of the skull. These are the scanned images of the skull. This is the rear portion. This is the side portion. This is the front portion. This is the top portion. This is the another side portion. And this is another top portion. So based upon this, the skull was reconstructed. Here we can see the diagram in the slide A, B, C, D. This represents the reconstructed skull using additive manufacturing to plan the operation. So they could plan the operation, how to cut the skull without damaging the internal parts, and how could they perform it uh, within short period of time, and what are the complications that they could avoid during the operations. So it worked as a rehearsal for them. So we can see the lines drawn on the skull as well. So coming to another example of the RP applications in the biomedical industry is craniofacial reconstructive surgery planning. Restoration of facial anatomy is required in cases of congenital abnormalities, trauma, or post-cancer reconstruction. The craniofacial reconstructive surgery, this means that restoration of facial anatomy. This facial anatomy is required in cases of congenital abnormalities. Congenital abnormalities are the birth abnormalities where the person would born with the deformed shape of the skull or the face. And also trauma. If there are any injuries to the skull or the facial parts, it would require a craniofacial reconstructive surgery. And also in some cases where the post-cancer reconstruction, if any tumors are there in the brain, that tumor has to be removed by taking off the skin first, which is on the skull, then the skull has to be removed, then the cancerous part in the brain has to be removed, whether it is in the brain or in the temple areas, it has to be removed. Then it has to be covered with the bone back with the implants, and the skin has to stitch. So while performing these operations, it would had defects in the facial parts. So the surgeries were essential to reconstruct these defects. In one such case, the patient had deformed jaw by birth, and a surgical operation was necessary to amputate the shorter side of the jaw and change its position. The difficult part of the operation was the evasion of the nerve canal that runs inside the jawbone. So one of the abnormalities was found in a patient that he had a deformed jaw. So this deformed jaw was by birth, and there was necessary to perform an operation to amputate the shorter side of the jaw and change its position so that it can be reconstructed. So difficult part of the operation was that the evasion of the nerve canal. So in the jaw side, we have a nerve canal. Inside the jawbone, we also call it as the root canal. Inside the jawbone, we have the nerve canal. So this is not visualized. So if you perform the operation without visualizing where exactly the nerve canal, it would lead to serious damage. So such an operation was impossible in the conventional procedure because there was no way to visualize the inner nerve canal. So in this slide, we can see the nerve canal which is present inside the jawbone. This yellow area, this represents the nerve mandibular canal, we call it as, this is the nerve canal. So using a CAD model reconstructed from the CT images, the computer tomography images, it clearly showed the position of the canal and simulation of the amputating process on workstations, and was a good support for surgeons to determine the actual amputation line. So by using the CAD model, which was reconstructed from the CT images, it clearly showed the position of the canal, and also the simulation of amputating process on the workstation was done, which provided a good support for the surgeons to determine the actual amputation line. So where exactly the amputation has to be taken place without affecting the nerve canal was easily identified by using the CAD model, which was reconstructed from the CT images. Furthermore, use of the resin type of the jawbone allowed the visualization of the internal nerve canal. Not only it had the helped the surgeons for amputing the jawbone, but also as the jawbone was made out of a resin prototype. A resin prototype is normally a semi-transparent prototype where we can see the internal structures in detail. So this semi-transparent prototype facilitated the determination of the amputation line and enabled an efficiency surgery simulation with an actual tool. So that's how the craniofacial reconstructive surgery planning was done effectively with the help of the additive manufacturing. So in this slide, we can see the CAD model from the laser scanner data of patient's facial details. So we can reconstruct the facial details of the person as a CAD model. And also this image shows us the SLA model of a patient's facial details. So this is the stereolithographic model, apparatus model of patient's facial details. In another example of additive manufacturing in biomedical industry, we will be talking about biopsy needle housing. Biomedical applications are extended beyond design and planning purposes. Not only how to design and how to plan an operation, but also it is extended beyond that. In what way, we will see in these coming slides. The prototype can serve as a master for tooling such as urethane model. Now we can create the prototypes which can serve as a master for tooling as a urethane mold. At Baxter Healthcare, a disposable medical products company, designers rely on two RP processes, that is SLA and SGC, to create master molds from which they develop metal castings. Additive manufacturing can also be used for the tooling purposes. Tooling purposes in the sense, in the mechanical engineering sense, we can create parts, we can manufacture different products. To manufacture different products, one of the conventional method we use is the casting. To create a casting, we require a pattern. That pattern, which serves for creating more number of products, we call it as the master pattern. So that master pattern in this application was created using two RP processes. The two RP processes are SLA and SGC. SLA again, it stands for standard lithography apparatus, and SGC stands for solid ground curing. These are the two methods of manufacturing additive manufacturing products. The masters have served as a basis for multiple sub-tooling processes. For example, after a master mold has been generated via one of the RP machines, The engineers might build a urethane mold around it, cut open the mold, pull out the master, then inject the thermoset material into the mold to make the prototype parts. So one of the method to make a master mold is to generate this model via one of the RP machines, as it was mentioned earlier, by using any of the machine. It can be SLA or it can be SGC. And engineers might develop a urethane mold, and when the engineers had cut that mold, then the master pattern was pulled out. Now we can inject the thermoset material into the mold to make other prototype parts. So in order to analyze how a biopsy model looks like, in this slide, we can take a look into the biopsy needle. So this is the biopsy needle, and this is the biopsy needle housing. These housing were created using rapid prototyping technologies. The general application of biopsy is that to pull any lump in the human body with a syringe. So this syringe is generally of longer length to go deep into the tumorous area. If you can look into the figure, this figure A, here we have a 3 mm conventional punch biopsy, and we have a syringe needle. When we pull this trigger, it pulls the cancerous or non-cancerous material, whatever is present in the human body. So this is the microbiopsy. And here the conventional biopsy, this is the material which was pulled out using this needle. And nowadays the microbiopsy is also being utilized, where the hole created is very micro in nature. Coming to another application of rapid prototype is the knee implants. Engineers at DFU Incorporation, a supplier of orthopedic implants, have integrated CAD and RP into their design environment, using it to analyze the potential fit of implants in a specific patient, then modifying the implant design appropriately. The DFU Incorporation, it is one of the orthopedic implants suppliers. They have integrated the CAD and RP into the design environment, and they could analyze the potential of how the implants have fit into that particular patient, and if any designs are required to modify, they would do it appropriately based upon their analysis. And also at DUFI, SLA plays a major role in production process of all the company products, standard and custom. The prototypes are also used as the masters for casting patterns to launch a product or to do clinical releases of a product. For this application, there are several advantages over traditional casting tools. At DUFA, they have not only analyzed the potential fit of the implants in a specific patients, but also they have created the prototypes which can be used as the masters for the casting patterns. And with this, they had several advantages over traditional casting tooling. First is the typical 10-week lead time is reduced. The manufacturing time was reduced for 10 weeks. Second, the cost of about $8,000, which was reduced from $10,000. So second, we can see that secondly, the cost of about $8,000 to 10,000 is reduced too. So by using the rapid prototyping in the knee implants in a company called DUFE, which is an orthopedic implant supplier, they could reduce their lead time. Second, they could reduce the cost of the implants as well, which was initially It was $10,000 before using the additive manufacturing, and after using the additive manufacturing, they could reduce it to $8,000. That is, they could save that they have saved 2,000 US dollars. So in this slide, we can see few of the example of the knee implants. The knee implants are generally used by the surgeons on the patients who have deformed their knees, who have worn out their knees due to the age factor or other factors, other trauma factors. Scaffolds for tissue engineering. Another application of rapid prototyping in biomedical industry is the scaffolds for tissue engineering. Tissue engineering has been used to replace failing or malfunctioning organs such as skin, liver, pancreas, heart valve leaflet, ligaments, cartilage, and bone. So tissues are generally present in the skin, in liver, pancreas, heart valves, and the other parts as mentioned in the slide. There were malfunctions of such organs. So this has given rise to the interest in applying RP techniques to build scaffolds, either to induce surrounding tissue and cell ingrowth, or serve as temporary scaffolds for transplanted cell to attach and grow into. If a patient has developed any malfunctioning of these organs, then the interest of applying RP techniques to build scaffold surrounding the tissue which was malfunctioning, or they could able to make a temporary scaffold for transplanted cells to attach and to grow onto. So these scaffolds can be designed in 3 dimensions on CAD, taking into consideration the porosity and good interconnectivity for tissue induction to occur. The scaffolds, during the time these tissues grow and the malfunctioning would disappear when the tissue completely grows. So these scaffolds were designed in 3 dimensions on CAD, taking into the consideration of the porosity and good interconnectivity of tissue induction to occur. In this slide, we can see the extrusion-based rapid prototyping technique, an advanced platform for tissue engineering scaffolds. You can see here the different types of scaffolds are being manufactured using any rapid prototyping. Different types of designs have been developed and analyzed, and upon analyzing which design is having good tissue engineering effect, that has been selected. So this diagram is been selected from the Biopolymers volume 97 issue 2 page number 8393 journal, which was published in the year 2011. Scaffolds for tissue engineering is that the function of cells such as in bone and cartilage regeneration is dependent on 3-dimensional spatial relationships. As such, the geometry of these hard tissues are critical to its function. RP has been able to lend itself to producing complex geometry fold. So we have seen in the earlier slide, to develop these geometries which would enhance the tissue engineering for proper growth of the cells. So 3-dimensional application is very much necessary to produce the complex geometry of the scaffolds. In this slide, we can see how the extrusion-based rapid prototyping techniques were used to perform or used to manufacture the scaffolds for the tissue engineering. Here in this diagram, we can see one of the RP technology where the scaffolds are formed here in the apparatus. This shows the schematic illustration of the generation of the scaffolds. Here we have the material supply. From the material supply, it goes into the nozzle. From the nozzle, the material is extruded in the geometrical shapes that are initially developed in the CAD system, from where it is converted to STL file, and from the STL file, it is converted into the machine readable format, and machine performs the fabrication process. In this slide, we can see different formed scaffolds with the different geometries. Again, this image is also taken from the journal which was mentioned in the earlier slide. Another application of RP was in customizing the tracheobronchial stents. Stents for maintaining the patency of the respiratory channels has been investigated for production using RP techniques. The stents that are used for the tracheobronchial applications rather. So in order to have the patency, in order to apply for the intellectual rights, RP technology was used effectively. The customization of these stents can be carried out to take into account compressive resistance with respect to stents wall thickness, as well as unique anatomical consideration. To produce stents, especially of tracheobronchial of nature, these stents are implanted or are made in the lungs. So in order to produce a good stent, it should take the compressive resistance, and as well as it should withstand the forces when the patient takes breath in and breath out. So taking into these compressive resistance, and according to the wall thickness, and according to the anatomical consideration, how exactly the original valves are there, based upon that the stent was developed, that was developed using the RP technique. So this picture shows the stents, the production of customized stents in slightly differing sizes for an ideal custom fit. So different stents have been developed. This stent has one shape, one size, one diameter. This stent has another. So this was a sprue. So based upon, just like the casting process, where the sprue is used to pour the material required for the process, and we have the parts here. Now these measurements are taken of the actual forces required to open the airway channel to its original dimensions. The CAD data is fed into the CAD system. The data is fed into the CAD system where modification on stent design is carried out. Upon confirmation, the 3D data is fed to an RP system where the master pattern of the mold is built. The master pattern then undergoes the silicon molding vacuum casting process, reproducing the stent master pattern with biocompatible material with all its strength, spring back, and anti-migration properties in place. Here we are using the silicon molding vacuum casting. The material used is a biocompatible material where it can have the strength, the spring back nature, and also anti-migration properties. All these things are tested and confirmed initially using the CAD data, and then it is fed into the RP system where the master pattern is produced using that technology. Another application of rapid prototype is in intervertebral spacers. Human spinal vertebrae can disintegrate due to conditions such as osteoporosis or extreme forces acting on the spine. So another problem in the human spine, a condition is called as osteoporosis or extreme forces acting on the spine. If you could analyze the situation, here in this slide, we can see that osteoporosis is a condition where the bone is of porous nature. In normal bone condition, the pores are dense, and we can see the density of the bone is more, and it can withstand high loads and everything. Whereas the osteoporosis bone is weak in nature, and this tendency is generally observed in the spines of the patients. So this kind of osteoporosis condition had led to the damage to the spinal bones of the patients. So in the management of such situation, a spacer is usually required as part of the spinal fixation process. So in order to manage this situation, a spacer was required to replace this porous bone, which is affected with the osteoporosis, which is very weak in nature. In this slide, we can see a spacer is built using additive manufacturing. So this spacer now, it will be working like a bone which can withstand enough forces So in the management of such situation, a spacer is usually required as part of the spinal fixation process. RP has been investigated for the production of such spacers, as it is an ideal process to fabricate 3D structures with good interconnecting pores for promotion of the tissue in growth. With the help of these spacers, the tissues also have been able to regrow. Other considerations for producing such an implant are that the material is biocompatible. So whatever the material that was produced in the additive manufacturing was biocompatible, and the mechanical compressive strength of the spacer is able to withstand the spinal loads as well. So these are the few advantages when the spacer was manufactured in the rapid prototyping machines. Another example is cranium implant. We have seen so far so many applications of rapid prototyping in biomedical industry. So biomedical industry is an industry where there is a vast scope for the additive manufacturing. So another application is the cranium implant. A patient suffered from a large frontal cranium defect after complications from a previous meningioma tumor surgery. We can see here, this is a tumor. Now this tumor has to be removed, and when the tumor is removed by the operation, by the surgery, now here the skull is deformed. This has caused the defect. So this left the patient with missing cranial section. Now the skull is missing here. You can see the deformation, the defect here. So due to the operation performed, and it could not fix the removed skull back into the position, so the deformation had taken place. And it has missed the skull in this area. This patient left the, this left the patient with missing cranial section, which caused the geometry of the head to look deformed, as we have seen in the previous slide. Conventionally, a titanium mesh plate would be hand formed during the operation by the surgery. One of the methods to, to remove this deformation in the patient's skull is to conventionally use a titanium mesh in the operation theater itself by using a titanium mesh. So this often resulted in inaccuracies and time spent for trial and error. So as the surgeon was using the titanium mesh in the operation theater there itself, so it resulted in inaccuracy, it resulted in consumption of time, because that was completely based upon the trial and error method. Using RP standard preparations of the patients were made and computed tomography CT scan of the affected area and the surrounding regions were taken during pre-operation stage. Now, in order to overcome that difficulty, the RP technology is now an effective method to improve the surgery. Is that pre-preparing in the prior to the operation, we call it as in the pre-operation stage, the CT scan of the affected area and the surrounding regions were taken. Then the three-dimensional CT data file was transferred to CAD system and the missing section of the cranium topography was generated. So whatever the affected area was there, that affected area was and the surrounding regions in the pre-operation stage, the CT scan was applied, and due to this CT images, the three-dimensional CT data file was transferred to CAD system, and the missing section of the cranium topography, we call it as the cranium topography, that was generated in the CAD model. After some software repair and cleaning up were carried out on the newly generated section, an inverted mold was produced and CAD. Software repair in the sense, there are few things that the CAD model that is generated in the RP system is not valid sometimes. So in order to make it a valid model, software has to repair its dimensions or some validations it has to perform, and after software repair it could generate the 3D model. This cranium implant, this three-dimensional solid model of the mold was saved in .stl format. As we have seen in the earlier video lectures, the data format after performing the 3D diagram, after getting the 3D image, whether you draw it using the conventional 3D software or you take it from the CT scan 3D data file, that has to be converted into a readable format where the additive manufacturing unit can understand. The generally used data format is .stl format by all the machines in and around the world. Now this has to be transferred into the RP system. The RP system that we are using is the SLS, that is the laser sintering for building the mold. The SLS mold was produced and used to mechanically press the titanium mesh plate to the required three-dimensional profile of the missing cranium section. Now, based upon this 3D data, whatever the data of that particular patient was there, it was given to the SLS machine. Now, SLS machine could perform the mold that can be used to cover the missing section of the cranial section of the patient. During the operation, the surgeon cleared the scalp tissue of the defect area and, and fixated the perfectly profiled plate onto the cranium using self-tapping screws. The, the scalp tissue was then replaced and sutured. At post-operation recovery, results observed showed improved surgical results, reduced operation time, and a reduced probability of complications. While applying the RP technology, it was that the operation was performed, the doctor has cleared the scalp and cleared the tissue, the defect area, and fixed the properly pre-profiled plate onto the cranium using self-tapping screws. Then the scalp tissue was again replaced and it was sutured. And when the patient was observed after the post surgery and after the recovery, the results showed an improvement in in the in the cranium defected area, and also the operation time that was used to perform the surgery was reduced, and the probable and the complications that could arise due to the conventional surgery has reduced as well. So we can see this is the representation of the cranial implant. The 3D section of the patient's skull was taken. This figure A shows the CT scan images, A, B, C. Then the 3D model was generated using the CT scan files in the CAD system. And this missing section was developed. This is the titanium plate is the material generally used for the implants. So depending upon the missing cranial defect, this titanium implant was manufactured and it was fixed using these screws. Then the scalp tissues were covered again, then sutured, then the patient was having his missing cranial part of the skull. So dear students, this was all about the RP applications in the biomedical industries in different ways. So far we have seen so many applications. In this session we have seen the additive manufacturing applications in the cranial applications, in the knee implant applications, in manufacturing of the biopsy needle applications. We have seen it in the performing or planning the skull operation, surgery operations. So I encourage all the students to do some review research in the nowadays performed biomedical applications using the additive manufacturing, where you can write a review article on the additive manufacturing applications in the biomedical industry, apart from these examples what we have seen in our lecture. Now we can say that there is an immense future and scope for the development of additive manufacturing in the biomedical industry. In the times of the coronavirus pandemic, now there is a need for additive manufacturing in the fight against the coronavirus. Now, the 3D printing society or the additive manufacturing society has responded to the current situation that you can see in this slide. The 3D printing in the times of coronavirus pandemic is that we could develop the mask, the safety mask using the 3D technology. We could develop a shield for the doctors, the frontliners who are serving us in these times of difficulty. Not only in India, around the world, the situation is really bad, and our frontline leaders, the frontliners, such as doctors, nurses, they required the face shields. So the 3D printing technology could manufacture a face shield which would help the frontliners, and also a 3D printed model where we can hold the sanitizer. This is also one of the application, one of the recent application of the 3D printing technology. And in this figure, we can see these are the 3D printed the ventilators to support the coronavirus patients breathing. And this is the goggles to wear for the frontliners, for the doctors and nurses when they visit the patients. And here, one of the company also developed a door handle. Instead of touching with the hand, they have developed a handle where you can use your forearm and pull the door. So these are the few recent applications of rapid prototyping or 3D printing or additive manufacturing, whatever the name is, all the same. So during the times of the coronavirus, in this pandemic, the 3D printing technology is helping out to the mankind in every way possible. So as additive manufacturing engineers, we are really proud of the efforts made by our peers, our colleagues, and our fellow beings in and around the world, in India and in around the world. With this, I conclude this topic of RP applications in biomedical industries. Thank you very much.